A spring of natural length A has one end attached to a fixed point A. The other end of the spring is attached to a package P of mass m. The package P is held at rest at the point B, which is vertically below A such that AB is 3A. After being released from rest at B, the package P first comes to instantaneous rest at A. Air resistance is modelled as being negligible. By modelling the spring as being light and modelling P as a particle, show that the modulus of elasticity of the spring is 2mg. So let's have a quick diagram of the situation. So the package is here, and we're going to have mg, and we'll have tension here. And if the natural length is A, then when it's in this position, we have an extension of 2A. This is the point that we called A in the question. And we know that the elastic potential energy is lambda x squared over 2L. And so we release it from here, and when it gets to here, the velocity is 0. And the compression in the spring at that point would be A. So the elastic potential energy that it has at the start, which would be lambda 2A squared over the 2 times A, the natural length being A, that's going to be equal to the potential energy that it has up here. Let's take potential energy as 0 down here at the bottom. And so it's risen a distance of 3A. So that's going to be 3mga. So it's going to be m times g times the distance risen, which was 3a. And then it will have some elastic potential energy at the top because there's a compression of A. So that will be lambda A squared over 2A. So simplifying all of this, we're going to have 2A lambda is equal to 3mga plus lambda A on 2. Let's multiply everything through by 2 so we're not dealing with fractions, and we'll get this. And then we've got an A that we can cancel out all the way through. And so we get 3 lambda is equal to 6mg, which gives us that lambda is equal to 2mg. And so that's part A of the question done. Now, what does part B say? Show that P attains its maximum speed when the extension of the spring is a half A, and use the principle of conservation of mechanical energy to find the maximum speed given your answer in terms of A and G. So if we think about B part 1, the max speed implies that T is equal to 0. Correction, T is equal to mg. So the forces balance out. The net force is 0. So if T is equal to mg, that gives me that mg is equal to lambda x over A, where x is the extension at this position. And therefore, mg is equal to, since we know lambda is 2mg, 2mg x over A. And we can rearrange that to give us that x is equal to A over 2. So that is B part 1. And then we need to do B part 2, which is where we're going to try and find the maximum speed. Now, when it's at that position, where the extension is A over 2, that means from this bottom position, it's gone up by 3A over 2. Since we know the total distance is 3A, and this would be 3A over 2 up here as well. So the gain in PE that's just going to be 3a over 2 times m times g. And so that's going to give me 3mga on 2. Now there'll be a loss of elastic potential energy. So think about the elastic potential energy that it had at the bottom when that's lambda 2mg and the extension was 2a. And now it's a position where the extension is a half a. So we just need to do some algebra here. And that is going to give us 8mg a squared over 2a. Take away 0.5 mg a squared over 2a. So that is 4 mg a. Take away 0.25 mga, which is 3.75 mga. So the gain in Ke must be equal to the loss of elastic potential energy, take away the gain in potential energy, which was this one here. And that gives me 2.25 mga. But we know that kinetic energy is a half mv squared. So that's got to be equal to 2.25 mga. And cancel the m's. And we get v squared is 4.5 ag. So v squared is equal to 9 over 2 ag. And that means that v would be 3 root ag over 2 meters per second. Now the very last part of the question just says state one way in which, in reality the spring is not light. State one way in which this would affect your energy equation in part B. Well, there's lots of things here. If the spring actually has mass, then the extension of the spring at equilibrium would be different because you have to take into account the mass of the spring below a certain position all the time. And that's just one of them. There's lots of ways that it would be different.